Okay, guys, this is Fall Probe 1, 2025, questions 11 through 15. So let's get started. What is the value of z? Question 11. What is the value of z in the solution to the following system of equations? Okay, so we're looking for z. We've got the system. We've got three variables, three equations. So whenever you have the same number of equations as you have variables, then it's solvable, right? So there are a bunch of different tactics to solving systems of equations like this. If you know anything about like how a matrix works, then there are some techniques around those, but you probably won't need to know any of those for the probe. At least I don't recall any questions where it's like that necessary or even like that much better to know anything about matrices. So I would not worry about studying matrices for the probe specifically. Instead, what you can do is a method called elimination. So when you've got like three variables and three equations, then you want to find some way to combine them together that makes them get rid of one variable at a time. So with linear equations like this, what that means is if you have like 3x plus 2y equals like 5, and then you have x plus y equals 3, right? Then the way that you could solve this, you could take this statement, x plus y equals 3, and multiply it by 2. So then you'd have 2x plus 2y equals 6, right? And if you compare these two, you'll notice that the difference here is that we have one x, right? We have this x here. If we detached it, then we would have x plus 2x plus 2y, right? But the goal of multiplying by 2 is to get rid of the 2y term here. So we can subtract these equations from each other, right? Since we have 2y in both of these equations, if we take the difference, then we'll have 3x minus 2x plus 2y minus 2y equals 5 minus 6, right? And so what that leaves us with, these 2y terms will go away, and then that 3x minus 2x will become just x, and then 5 minus 6 is negative 1, so we solve for x. But that's not our problem here, right? Basically, the idea is just get rid of as many things as possible. But since we're specifically looking for z, we want to think of a combination of these equations that will get rid of everything except z, because we want on the left hand side to just have some constant times z, and then that will be equal to some number, because then z will just be equal to that number divided by the constant, right? And the way we get that is by getting rid of x and y. Now this is lucky for us because if you look at the second equation, z minus x minus y equals negative 10, we have a negative x and a negative y already. So if we sum these two equations together, then it'll look like this. So we're summing the first and second equations together, meaning we'll take x plus y plus z minus x minus y equals negative 10 plus 36, right? And then you'll notice that the x and the y both go away. They sum to 0. So we get 2z equals 26. So that means that we can just divide by 2, so then z equals 13. Now that's a pretty easy problem because of just how it's set up, but the answer is A. Okay, number 12. So, in figure ABCD, in the figure, ABCD is an isosceles trapezoid with O the center of the circle, and the lengths as shown. What is the square root of the area of the trapezoid? Okay, so if you look closely, it being an isosceles trapezoid just means that this length is the same as this length, right? And this angle is the same as this angle, and this angle is the same as that angle, right? That's just what they mean. And what is the square root of the area of the trapezoid? Okay, so we want to find the area of ABCD. We can do that by finding a couple lengths here. So if we draw this right here, well, first of all, how do you find the area of a trapezoid? If you have a height, which is the distance between the two parallel sides, and then you have the lengths of the sides, so L1 and L2, right? Well, you average them together, L1 plus L2, and then you divide by 2 to average them, and then you multiply by the height. That's how you find the area of a trapezoid. And so we already have the two lengths here of the parallel sides, so we'll just have to average those and then multiply by this height, by the height of the trapezoid, which we don't know. But luckily for us, we got some right triangles here. So if we draw from the center to this BC right here, and we cut it in half, then 32 cut in half is 16. So now we have a right triangle with hypotenuse 34 and one leg 16. So how do we find the other length? We take 34 squared and subtract 16 squared. 34 squared minus 16 squared equals, here, I'm going to do a trick for this. 34 plus 16 times 34 minus 16, okay? 34 plus 16 is 50, and 34 minus 16 is 18, I believe. Yeah. So that would give us, well, actually, we're just trying to find the square root of this. And if you notice, we can take a 2 from the 18 and give it to the 50 to make, instead of 50 and 18, that's the same as 100 times 9. So the square root of 100 times 9 is the square root of 100 times the square root of 9, which is 10 times 3, which is 30. Okay? So we know that this length right here is 30. And we have a right triangle right now. And we know it's got hypotenuse 34, small leg 16, big leg 30. Okay. Now we're almost there. We just need this bit, right? We need this part of the height, which we're missing. We have this bit, it's 30, but we need that bit. Okay, so if we draw the radius from O to D, then you'll notice that its length has to be 34 since it's the radius. And then we're cutting 60 in half, so we get 30. But if you realize before, since this is a right triangle, this is the same right triangle we had, right? 34, 30, so the other side is 16. We don't even have to compute anything. So this is 16. So now we have to find, what are we looking for? The square root of the area of the trapezoid. So we need the square root of the area, which is the average of 60 and 32, this two sides, times the height, which is 30 plus 16. But we're taking the square root of this, right? So 60 plus 32 divided by 2 is the same as 30 plus 16. So we actually just have 30 plus 16 squared, right? And 30 plus 16 is obviously 46. So that's going to be the square root. So the answer is A. Okay, now question 13. This is kind of a difficult one because you need to know some trigonometry and you need to know not just a little bit, you need to know quite a few things about it. So sine of x plus cosecant of x. Let's just look at that squared. Okay, so cosecant of x equals 1 over sine of x. That's an identity that you should know, right? So we're going to replace cosecant of x. Actually, we're not going to replace cosecant of x. We could, and you very well could solve the problem that way, but I'm not going to, right? I'm going to do it this way. So notice that cosecant of x, since cosecant of x is 1 over sine x, that means that sine of x times cosecant of x equals sine of x divided by sine of x. And so when it's not 0, that means that we get 1. Okay, so in general, sine of x times cosine of x is 0 when they both exist. Or it's equal to 1. Sorry, not 0. It's equal to 1. Okay, and that's just good to know in the back of our mind. So sine squared of x plus 2 sine of x times cosecant of x plus cosecant of x squared, that is equal to sine squared of x plus, remember, sine of x times cosecant of x is 1, so plus 2 plus cosecant of x squared. We can't simplify this anymore. We can write it in different ways, but we can't simplify it yet. So let's move on to cosine plus secant. So secant is also 1 over cosine. So that means if we have secant times cosine, then we get 1. Same deal as before. So we're going to expand this. Cosine of x plus secant of x squared. And you could just say, since this is the same situation where if you multiply these two together, you get 1, you could just replace sine with cosine and cosecant with secant, and you would get the same thing, which is true. So we're going to get, sorry, not sine. We're going to get cosine squared of x plus 2 plus secant squared of x, right? That's another part of what we have. Okay, it's good to remember. What's our last bit? So we're going to be subtracting this, but let's compute it first. It's the same situation again, but it's slightly different. So tangent of x minus cotangent of x squared. So cotangent is 1 over tangent. So it's kind of similar to what we had before. So if we compute this, we get tangent of x squared minus 2 tangent of x times cotangent of x plus cotangent squared x. And then that is going to be equal to just minus 2, right? So tangent squared plus cotangent squared. But remember, we're subtracting this. So our whole sum, we have this part that we're adding this part, and then we're subtracting this part. So we're going to end up with sine squared of x plus 2 plus cosecant squared of x plus cosine squared of x plus 2 plus secant squared of x plus, minus tangent squared of x plus 2, because we're subtracting negative 2, minus cotangent squared of x. Okay, and then there are some other identities that come into play here too. So sine squared of x plus cosine squared of x is equal to 1. That's the Pythagorean identity. So we can cross these two out and just get 1, right? So we have 1 plus 2 plus cosecant squared plus 2 plus secant squared minus tangent squared plus 2 minus cotangent squared. So we've got 1 plus 2 plus 2 plus 2 And then secant squared minus tangent squared is also equal to 1. All of these come from the Pythagorean identity. They just depend on whether or not you're dividing the whole thing by cosine squared or dividing the whole thing by sine squared. But it's all the same. It's all from the same formula. And then same deal. Secant squared of x minus cotangent squared of x is also equal to 1. And then actually I'm gonna check that one. So cosine squared of x plus sine squared of x equals 1. Okay, how do I check secant squared minus cotangent squared? So I'm going to have to divide everything by sine squared to get that secant squared term. Which is going to be, so we're going to get secant squared of x minus 1. Oh wow. Where were we? We had sine squared plus cosine squared plus 2 plus 2 plus 2 plus we were here. We had secant squared minus tangent squared equals 1. And we were just verifying that cosecant squared minus cotangent squared equals 1 too, which is true. So we're going to add 1 for both of those as well. Sine squared plus cosine squared, we already know, is equal to 1. Cool. So what does this all add up to? It simplifies nice and neat to 9, right? So it's saying what is the smallest possible value. This is actually the only value that this can take on where the expression is defined. So it's either 9 or it's not defined, so it has to be the smallest possible value too. So that one is done. Okay, question 14. The polynomial t to the fourth minus 3t cubed minus 15t squared minus 6t plus 4 has 4 distinct real roots, r1, r2, r3, r4. What is r1 plus r2 plus r3 plus r4? Okay, so for you mathful people, this will be a no-brainer. You will instantly get it because you know Vieta's, this is how you spell it, Vieta's formulas. Now, you need to research these if you don't know them. They're super simple, they're easy to remember, but I'll show you a way that you can get this problem without needing to know this. So this isn't the kind of problem where you need to know a certain formula or you can't get the points. There are problems like that, like question 13 with the trigonometric functions and stuff. If you're not familiar with trig functions at all, then there's no way for you to get that problem, which is fine. That's just one of the problems that you skip. You can't answer every question. No one gets 100 every year, right? So don't feel bad about that at all. If you don't know trigonometry, then you don't know trigonometry. If you want to study trigonometry because you think that it will help you on the test and you're yet to take a trig class, then that's fine. Plenty of people do that too. So you won't be ill-prepared when you come across questions like that. But it's also not your fault for not being prepared for that. So don't feel bad. But Vieta's formulas are easy to learn and you need to know them. If you've done any math bull at all, you'll know what I'm talking about. They're really quick ways of computing if you have a polynomial, stuff like the product of the roots, the sum of the roots, stuff like that. But, so we have the polynomial like this, and we're given its roots. So another way to write that polynomial would be like this, right? Notice that it's monic, which means that its first term is coefficient 1. So if we say that these are the roots, then if we write it as the product t minus r1 plus quantity times t minus r2 plus quantity times t minus r3 times t minus r4, that it's equal. It's the same thing, right? And what that means is that if we group our terms properly, then we're going to be able to compare things, right? And so one of those things that we're going to group, if we want to be adding these all together, then we're going to want each of them to occur once, right? We're going to want each root to occur one time in our multiplication. Because that might sound scary, but I'll show you what I mean. So if we multiply, let's say we want r1 minus r1 times t times t times t. So we're gonna have minus r1 times t cubed, right? This is the little bit of the t cubed term, and then if we say we have r2, we have minus r2 times 1, 2, 3 t cubed. Sorry, minus r2 times t cubed, and then we'll have this one right here, minus r3 times t cubed, and then minus r4 times t cubed. That all factors to negative r1 plus r2 plus r3 plus r4 times t cubed. And notice that it's attached to a t cubed term, right? So remember, we can match these up because they're exactly the same thing, because it's saying that these are the four roots, right? So we're allowed to write it like this. They mean the same thing, right? This is our t cubed term, but so is this. So is negative 3t cubed. That means that negative 3t cubed equals negative 1, sorry, yeah, well, technically, negative r1 plus r2 plus r3 plus r4 times t cubed. And if we divide off the t cubed and we get rid of that negative sign, then we'll have 3 equals r1 plus r2 plus r3 plus r4. So that is going to be our answer, A, 3. Cool. Okay, question 15. A bridge is made of 110 wooden planks in a line. Alice and Bob are standing at the leftmost and rightmost planks respectively. Alice walks right, stepping on every third plank. Bob walks left, stepping on every fourth plank. Each continues until leaving the bridge. How many planks are stepped on by both Alice and Bob? Okay, so where is Alice? Alice is on the leftmost plank. So she's on plank number 1. That's Alice. We're going to number all the planks from 1 to 110. This is going to be plank 110. This is going to be plank 2, 3, 4. This is going to be plank 109, 108, 107, and 106. Okay, and this is where Bob is. And Bob jumps by 4, right? Alice jumps by 3. So she's going to step on the first plank, the fourth plank, the 7th plank, and so on. Bob is going to step on the 110th plank, the 106th plank, the 102nd plank, etc. So Alice is going to step on the first one, and then for however many steps she's on, so if she's on step 0, then she'll have moved 0 times 4 spaces to the right. But if she's on step S, she'll have moved 4 times S spaces to the right. So she'll step on all of them, all of the planks of the form 1 plus 4S. So if you can write a number like 1 plus, she steps on every third one. 1 plus 3S. Yeah, that's right. Alice steps on every third plank. So if you can write a plank in the form 1 plus 3S, where S is an integer, a positive integer, or a non-negative integer, I guess, because 1 counts, then Alice will have stepped on it. Okay. What does that mean? That means she stepped on plank 1, S equals 0. For S equals 1, she stepped on plank 4. S equals 2, she stepped on plank 7. S equals 3, she stepped on plank 10. And then that's just a way to count it, right? Okay. And then Bob is stepping 4 to the left every time, right? He starts at 110, and then we subtract 4 from the plank that he's on for every step that he takes. right? So all of his planks will be in the form 110 minus 4s, right? So if Alice steps on every plank like this, and Bob steps on every plank like this, we need to find how many they both step on simultaneously. So that means looking for every number from 1 to 110 that is in both of these forms, right? And that doesn't mean setting them equal. Here, I'll change that s to a k for Bob, okay? What that means is that you can write the number as 1 plus 3s and as 110 minus 4k. Okay. So there are many different ways we could go from here. One of them is noticing that it doesn't really matter where they start as long as they step on all the planks like of that form, right? So Bob could start at the last plank that he steps on and then go right every 4, and he would still step on every plank that he stepped on before. So do you see what I mean? He's just reversing his steps. So what is the last plank that Bob will step on? So we want to get as close to 1 as possible with 110 minus 4k without going under. So at k equals 26, that's 104. At k equals 27, that's 108. So when k equals 27, so after he's stepped on a total of 28, because we're including this one, after he stepped on a total of 28 planks, which is the total amount that he steps on, he'll be on step 110 minus 108, which is step 2. So Bob will also be starting, it'll be analogous to if Bob started at step 2 and then stepped forward every 4. So it'll be 4k plus 2. Okay. So we want every number that's 1 plus 3s and 4k plus 2. So let's say n equals 1 plus 3s. Okay, so it's another way we could write that is n is congruent to 1 mod 3. Okay, so n is congruent to 1 mod 3. But n is also congruent to 2 mod 4. Okay? So n equals 1 plus 3s, but also n is congruent to 2 mod 4. So if we replace n there with 1 plus 3s, then we have 1 plus 3s is congruent to 2 mod 4. So 3s is congruent to 1 mod 4. Okay, so 3 times a number is congruent to 1 mod 4. So 3 times a number is going to be 1 more than a multiple of 4. So if we multiply both of these sides by 3, right? Sorry, let me get this out of the way. If we multiply both of these sides of this congruence by 3, then we get 3 times 3s is congruent to 3 mod 4. So 3 times 3s is 9s, which is congruent to 3. And the reason I multiplied it by 3 is because 9 is 1 more than 8, and 8 is divisible by 3. So that is also 8s plus s is congruent to 3 mod 4. But 8s is always going to be congruent to 0 mod 4, so we can just erase it, because it's 0. So s is congruent to 3 mod 4. So s equals 4t plus 3. Okay, now if we return to n, remember that n equals 1 plus 3s, but s equals 4t plus 3. So n is also equal to 1 plus 3 times the quantity 4t plus 3 times the quantity 4t plus 3. So n equals 1 plus 12t plus 9. So n equals 13t plus, sorry, not 13t, what am I doing? N equals 12t plus 10. Okay, so every number in the form 12t plus 10 from 1 to 110, we would count. We would say that works, okay? So now all we need to do is find how many of those there are. So if t is equal to 1, then we have 22. So this is saying that 22 is the first time that they step on the same, so t equals, actually t could be 0, right? Are they both going to step on 10? If we step on 4, we're going to step on 7, and then we're going to step on 10. So A steps on 10. B goes from 2 to 6 to 10. So they both step on 10. So when t equals 0, that's our first time that we meet. Okay? We need to find the biggest t that we can like fit into that bound of 110. So we need the biggest t that 12t plus 10 is less than or equal to 110. So 12t is less than or equal to 100. So t is less than or equal to 100 divided by 12, which is, if we think about the floor, if we think about what is the biggest number that's less than or equal to 100 divided by 12, that's a whole number, what would that be? Well, 12 times 5 is 60. 12 times 7 is 84. 12 times 8 is 96. And if we go to 9, then that's too much. So when t equals 0, 1, 2, 3, 4, all the way up to 9, then, or sorry, all the way up to 8, then this works, right? So that means that they'll meet for every t from 0 to 8, okay? How many t's are there from 0 to 8? Well, it's the same as however many numbers there are from 1 to 9. 1, 2, 3, you're just counting, so it's 9. So the answer is E. Okay, that one was kind of tricky, but there were some other ways to do it too. But that was just the way that worked best for me. And the takeaway there is that modular arithmetic is really helpful, although technically you didn't need it for this problem. So just keep that in mind. This set of problems had some tough ones, but it also had some doable ones. So this one, all that you need to do is study Vieta's formula, and if a problem like this shows up, then you'll get it. This problem, all you need to do is recognize that to get rid of x and y, you just need to add these two equations together to get rid of those and isolate z. And this one was a little bit trickier of a geometry problem, but we figured it out just fine. And then this one definitely took some trigonometry, and this was a nice number theory problem. Okay, well, that was a good 5 problems.